Hey everybody, it's Ripley back again. I think I discovered my lagging, a fix to my lagging problem. My mathematical lagging problem. I look at this. I've made my little dangle a little bit thinner here as far as the thickness of my writing. So I think that may have fixed things. In 13.1, I'm going to teach you guys how to count. You know, 1, 2, 3. Just kidding. What we're really going to do is we're going to do a little bit of set theory real quick. We're going to talk a little bit about how sets work. Ooh, that does work a lot better, doesn't it? Theory. Okay. Think of a set as being, we just got ourselves a set. The way I think about it, and I had a kid explain this to me, and it totally made sense. It's a box, all right? It's just a box with stuff in it. So I'm going to call this box the box filled with the letters A, B, C, and D, okay? And sets are typically denoted with capital letters. So this would be like set A, all right? Now, we have something called a subset. A subset. Now, there's proper versus improper. It's either proper or improper. And I'll show you there's some notation here. It's just, again, just more learning of the language. I can say that a subset is, or that a set is a subset of another set. And I use it this way. Let's say that A is a subset of B. Now, this notation right here, it's not a C. It's almost like an intersection turned on its side. This says A is a proper subset of B. Now, let me explain what proper subset versus improper subset is. If I think about it, I can say that, I can say that A is a subset of itself, but it's not a proper subset of itself because A is itself the set that we're talking about. So a proper subset means that we can't include the set itself. Now, I may not be making a whole lot of sense, but let's do the subsets, the proper and improper subsets of this set that we have right here. All right, the first subset of any set, and the one that you have to know about, is the empty set, and that's just this guy. The empty set is the set that contains nothing in it, which the empty set and the set itself is a subset of every set. That's sort of crazy, but it's really true. All right, so that's the first subset. Another subset is all of the singletons. So I'm going to have A, I'm going to have B, I'm going to have C, and I'm going to have D. These are all proper subsets of set A. In other words, they're not the set itself. Now let's think about the doubletons. So I'm going to have the set A and B, right? I'm going to have the set A and C. I'm going to have the set A and D. All right, so that picks up all the sets. Now, order doesn't matter, right? So the set that contains D and A is exactly the same set that contains A and D. Not deoxyribonucleic acid, DNA. Anyways, math is fun. These are proper subsets because it's not the full set A, B, C, D. All right. Ooh, I've got some doubletons I missed, right? I got B and C, and then I've got B and D, B and D, and then I think I'm just missing C and D. Those are my doubletons. All right. Now, this could be kind of a pain in the butt, but here come our tripletons. So I got A, B, C, right? I got A, C, D, right? What else am I missing? And I've got B, C, D. Is that right? A, B, C, A, C, B, C, D. B, C, D. Does that catch them all? No, of course not. Because I've got A, B, C, A, C, D. Oh, what else did I miss? I've got A, B, D. A, B, D, in addition to my A, D, H, D. Oh, that's bad. All right, I think that picked them all up. Yeah, it should, because there should be as many of these tripletons as there are singletons, so there are 4 of them. And then last but not least, there is the entire set itself. Now, the entire set, this guy, is not a proper subset of A. It's an improper. And you can kind of see the way in which the notation was generated or invented or whatever the heck you want to call it. It kind of works like a less than versus less than or equal to. All right? So this is equal to A, so it can't be less than A. All of these sets have less elements in them, and elements are what we stick in sets. We've already talked about them. Now I want to show you something here. Let's count the number of subsets that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. What do you notice? There were 4 elements in the set to start, and there were 16 subsets. So let's see if there's some correlation between the number of elements in a set and the number of subsets. Let's do another one, just real quick. This won't take long. How about B equals AB? Right? Those are my elements, just A and B. So my subsets are going to be the empty set, singleton A, singleton B, and then the whole set itself. Again, not a proper subset, but still a subset of B itself. 1, 2, 3, 4. Wait a sec. So wait, when n equaled 4, the number of subsets of subsets equaled 16. When n equaled 2, the subsets equal 4. I'm starting to see the thing here. So if n equals the number of elements, in mathematics we're lazy, so we shorten everything up. Number of elements in a set, this implies, maybe it didn't solve my lagging problem, that 2 to the n equals the number of subsets. I kind of like the way it writes though better. You guys let me know if you don't like the thin stuff. I can always go back to the fatty. The number of subsets. All right, well, that's cool. We got ourselves a rule, which is awesome. Okay, now let's take a deep breath here. I'm going to introduce a concept, and I know you've seen it before. It's called the Venn diagram. And the Venn diagram is incredibly helpful. Venn diagram is awesome. So what it is we think about if we're dealing with more than one set. So this is just regular old set A, okay? And then we've got, let's say we got set B, and let's say that they at least the way we're going to draw it, they're going to overlap. So they're going to have this intersection point right here. All right, so set A and set B. Okay? Now, I need to introduce a little bit of notation here. There's a notation where I do this little script N looking thing, which I'll probably forget to make it look all pretty. N of A, this is called the cardinality of A. Cardinality, which is a fancy word. I don't even think your book uses it. Cardinality of A. Cardinality of A. All right, and which just really means the number of elements. Number of elements. Okay? And then NB is same thing. Number of elements. I guess this is in A, and this is number of elements. Whoa, number of elements in B, etc., etc. All right? So that's just a notation that we're going to use. Now, let's think about how this is going to work. If I want to try and figure out if counting is all about really counting the number of elements that are in something. Let's say that set A has 100 things in them. All right? And B has 50. All right? But let's say that A has 75 here and it's got 25 here. Now, what would that imply about the things that were in B but not in A? So we could clearly define each one of these regions, right? If I live here, I'm in A but not in B. If I'm in here, I'm in both. And if I'm in here, I'm in B but I'm not in A. So if I've got 25 elements in the intersection where A and B overlap, then how many do I have just in B? Well, the answer to that is obvious. Okay, there's nothing to it. So if I want to figure out the number of elements in the union at A union B. Now, think of the union as being like an or statement. All right? So how many things live in either A or B? Well, that's easy to do, right? Intuitively what we're going to do is we're going to add up the number of elements in A, and then we're going to, or with the number of elements that are in B. But there's only one problem. The elements that are in both A and B were counted twice. They were counted in A, and they were counted in B, right? So when I said, okay, this is 100, well, 25 of that 100 were out of B. So when I count all the elements in B, I've counted those things twice, and I don't want to do that. So what I do is I subtract out the number of elements that are in their intersection because they got counted twice. So I subtract out one set of those. All right? Now, let's make sure everybody knows this notation. This guy right here is union. And in set notation, think of this as OR. This guy right here, this upside down U without a little kickstand, is intersection. Intersection. And in set notation, we can think of it, or excuse me, in set parlance, we can think of it as being AND. All right, so this is the number of elements in both A and B. This is the number of elements in A or B. But parenthetically, let's throw a little both in there too. So or both. A or B or both, because we have to include that in there. All right, now what if the number of elements in A intersect B is empty? There are no elements in there. Well, what would that imply about the Venn diagram? That's an easy Venn diagram to draw, isn't it? Here's A. If their intersection is empty, that really just means that they're two distinct sets, right? In this case, their intersection is empty. So that makes life simple. Then the number of elements in A union B, since it's empty anyways, think of the empty set as being the set equivalent of 0. That's how it works. We're just talking about sets here, though, rather than numbers. So it's just the number of elements in A plus the number of elements in B. Nothing to it.